In this video, we will discuss Principal Component Analysis, or PCA for short. In this video, we will review standardizing data, provide an overview of Principal Component Analysis, or PCA, in the context of autoencoders. This video will give you an intuition how autoencoders work, and you can also use PCA and related methods to improve the performance of your neural network. Standardizing data. In this section, you are going to use rectangle tensors or matrices. Each sample is a row in a matrix. In this example, we have 4 samples. We will give the data 0 mean. We can accomplish this in PyTorch as follows. By first calculating the mean for each column. We get a 1 by 2 vector. Each element contains the mean for that particular column. Then subtract the mean from tensor x and reassign it to tensor x. The data in X now has a 0 mean. The vector mu is the mean. We simply subtract this vector from every data point centering the data at 0. The data should have 0 mean while performing PCA. In general, you should standardize your data by subtracting the mean from each column and giving each column a standard deviation of 1. We can calculate the standard deviation as follows. We add a small value to avoid division by zeros. This will give us the standard deviation of each column. To standardize the data after we subtract the mean, we divide each element in a column by the standard deviation of each column. We can accomplish this by multiplying the mean by the inverse of the diagonal matrix D. Each diagonal element is the standard deviation of the corresponding column. In PyTorch, this is just one line of code. Standardizing the data is preferable, but not necessary for PCA. If your dataset is smaller, you can also use sklearn to standardize your data. In this example, we standardized our testing or validation data using the mean or standard deviation from our training data. Check out the labs for more. The process squashes the data, making each access have the same scale. Generally, we should standardize our data before we train our network. Now, let's discuss PCA. We will only provide an overview of how PCA relates to autoencoders and how it can help you train your networks. In this video, we will only discuss 2-dimensional and 3-dimensional cases, but everything can extend to multiple dimensions. In this example, we have a 2-dimensional plane. As long as the 2 vectors are not pointing in the same direction, we can represent any data point in that plane. These vectors are the basis. If the vectors are perpendicular, i.e. orthogonal and have a unit length, they are an orthonormal basis. PCA allows us to find a good orthonormal basis for a dataset. In PCA, we assume that there is a set of vectors that generate the data, and the rest is redundant. For example, in 2 dimensions, we have one vector q. We assume our data is a scalar multiple of q, where z is the code. We then have some noise added to the data perpendicular to q. We assume the same for the second sample. We do this for multiple samples. We assume the majority of the magnitude or variance of the data is in the direction of vector q. We can use PCA to find this vector q. We also have a second direction perpendicular to q. This direction should be redundant. We can extend the idea for more dimensions. Let's do a 3-dimensional case with 2 vectors. We assume the data points or feature vectors can be represented as a combination of q1 and q2. As a result, all the data points must fall on the following plane. Like the previous example, we assume that there is some noise that offsets the data from the plane. Finally, we have the q3, perpendicular. The idea is that this direction is not that important for the data. Let's see how to write the data points x1 interims of q1 and q2. First, we find the projection x1 on q1 and q2. This is the code in an autoencoder. The point x1 hat is simply the point written interims of q1 and q2 and falls on the plane. This would be the output of your autoencoder. We would like to determine q1 and q2 that minimize the difference between x1 and x1 hat. For just the point x1, the plane would look like this. Let's see how to determine the expression for the plane for each point using matrices and determine the best basis q1 and q2. We place basis vectors on the matrix Q. We can find the projection onto each plane by multiplying all the points x by the matrix Q transpose. In autoencoders, this would be our code. The actual point on the plane can be found by multiplying the result by the matrix Q. This is the approximation, so we call these points x hat. We would like to find the best Q that minimizes the difference between x and x hat. We can do this by finding a matrix Q that minimizes the error between x and x hat. That is, just a cost function. If we assume the vectors in Q are an orthonormal basis, we can solve the problem in a few steps. If our data has zero mean, we calculate the covariance matrix C with one line of code in PyTorch. We can obtain Q by performing eigendecomposition of our covariance matrix, where the eigenvectors in Q and eigenvalues in the matrix lambda are shown here. In PyTorch, we can calculate the eigenvalues and eigenvectors as follows, where the output of eigenvectors is identical to Q, but the tensor eigenvalues is just one dimension. We will clarify this with an example. Each eigenvector has its own eigenvalue. If the eigenvalue is ordered, it means that they are arranged from largest to smallest. The smallest eigenvalue corresponds to the direction of lowest variance, in this case Q3. To understand the relationship between Q1 and Q2, let's take a look perpendicular to the plane. From this view, we see that the horizontal direction has less spread or variance. This is the direction of Q2, or the eigenvector with the second largest value. The vertical direction has more spread or variance. This is represented with Q1, or the eigenvector with the largest value. In general, we can select a different number of eigenvectors depending on what task we would like to accomplish. See the labs for some examples. Let's do an example in PyTorch. We have the tensor x. We can visualize the data as follows. We can subtract the mean from the data. We calculate the empirical covariance matrix. We can calculate the eigenvalues and eigenvectors. The eigenvectors are the columns of the tensor. Each row of the tensor eigenvalue is an eigenvalue representing the diagonal element of lambda, where the first element is the real part and the second element is the imaginary part. In this case, it will always be 0. The eigenvalues are not ordered. We can find the corresponding eigenvector for each eigenvalue as follows. We can obtain the code by performing the following matrix multiplication. We transpose all the operations, as all the rows in Z and X are samples. It should be noted that all the columns in Z have 0 correlation with each other. We can find the projection back or the output as follows. As we use all the eigenvectors, it's a perfect reconstruction. We can also find the max eigenvalue. We find the corresponding max eigenvector. To keep the tensors the same shape, we simply copy the eigenvector to a new tensor. This behaves like setting the other eigenvector to 0. We find x hat. We can see all the samples fall in the same line. This time, as it's an approximation, all the points fall on the line that is a scalar multiple of our eigenvector. We should perform PCA our data before we train our network, using the code as the input. This will generally improve performance. You can perform PCA in sklearn for smaller datasets. Here is an example with sklearn. Standardizing your data before or after PCA is called whitening and will further improve your training performance. This can also be done with sklearn to whiten your data. If our dataset has too many samples, we can calculate the covariance matrix as follows. To perform PCA, if there is a large amount of features, we must resort to iterative methods or autoencoders.